to your liking. Let me start. So just to confirm, you can see my slide transition, right?
We can see it. Yeah, it works.
Excellent. Thank you. Okay, so I will talk about how to do light transport simulations under a rather more rigorous physical principles compared to the typical computer graphics application, specifically how to do wave simulations. My focus is on light transport simulation in complex scenes and environments. As a motivation, think about a car with optical and non-optical sensors like radar on a road, and we would like to simulate how these sensors perceive the complicated environment for development, validation, and training of driving assistive technologies. Otherwise, for simulating the signal coverage of cellular radiation in a city, right? There are other applications like acoustics, which are less of a focus at the moment, but also very interesting future developments. All right, okay. My research has focused on adopting computer graphics tools, specifically path tracing, to this kind of applications, because it is these computer graphics tools that have been proven to scale to the massive scenes that I care about, and where other tools, existing wave tools, simply are nowhere near as scalable to be able to be used for those kind of environments. So I will give a high-level overview, hopefully to get to mostly pique your interest. You're always more than welcome to talk to me and check the existing work. I will be discussing ongoing and in development work. So let me start with a brief overview of path tracing. Path tracing is a family of techniques that aim to simulate the light propagation interaction in a scene. And path tracing is often indeed what is used to render the realistic images that we see in animated films and movies. Path tracing does particle-based simulations, where these trajectories of particles of light are traced in order to form paths that connect an emitter to the sensor, and then by summing up the contribution of many such paths, we Monte Carlo integrate for the light transport through the scene. The meaning of particle of light I keep opaque on purpose. Classically, it is a point in the Hamiltonian phase space of ray optics, so a classical ray of light. But as I will briefly touch upon later, it can be generalized, and we should simply understand it as a packet of light energy that we can trace and simulate. As with any Monte Carlo integration scheme, convergence is usually rather poor, and variance reduction techniques like properly combining multiple important sampling strategies are crucial for the practical simulations, are crucial for actual practical convergence. In computer graphics, there have been significant research on path tracing, and with a lot of focus on sophisticated sampling tools. And I would really like to not lose these amazing tools that have been developed in computer graphics as we generalize path tracing to the applications that I care about. And that is a primary motivation. So probably for this audience, this is less relevant, but this is designed just to show you the output of a typical offline path tracer, where the high-dimensional Monte Carlo integration needs to integrate over the spatial, angular, spectral sensitivity of the sensor over the entire path space and multiple emitters. And the point is that convergence can be, in practice, slow. So you can see where this is going, but getting rid of all that noise will take quite a while. The most important question that we should ask as we want to generalize path tracing is what actually makes classical path tracing powerful? And that's probably the most important part of today's presentation. I would argue that the following two properties are the key: locality and incoherence. And I will explain. Locality means that each light particle exists at a singular position, well-defined singular position, and propagates into a singular, well-defined direction. What this means is that a Monte Carlo sample will typically only interact with a tiny fraction of the scene, right? And light matter interactions need only be defined at singular positions of ray intersection with geometry. It simplifies the formalisms considerably. It also means that we may use spatial data structures to algorithmically accelerate the propagation part, right, the ray tracing part. Today, it's even accelerated by hardware and can be done extremely fast. Incoherence means that light particles add up linearly in terms of their power, or in terms of power-derived units like radians. This means that once we find good high contribution passes, the contribution of such a pass is always going to remain part of the solution. You add it to the solution, it's always going to be so. It cannot be annihilated, for example, via destructive interference via another particle. So incoherence means no interference. And incoherence is key in allowing us to do good path sampling. I would claim that path tracing should actually be defined as algorithms that do local and incoherent particle-based transport. So classical path tracing, that should be the definition. Those two properties are instrumental for these algorithms. If you're familiar with the path-space integral formulation of light transport, then clearly these two properties follow directly from the formalism, right? Passes are by definition a sequence of points, so they're just ray passes, and their contributions add up incoherently. All right, so this is classical path tracing. I will come back to the path-space formulation a little bit later. So when we are confined to a local and incoherent light transport framework, what kind of physics can we simulate? So clearly it would be some superset of ray optics, right? So in addition to simulating ray optics, we can also simulate some phenomena that strictly depart from ray optics, like some spectral effects, like color or even fluorescence. Polarization can be simulated very well. And some light matter interactions, be it the Fresnel coefficients or thin film interference, all those things depart from ray optics. So classical path tracing is a little bit more powerful than classical ray optics. And this is a very interesting question. What can actually be simulated? To my knowledge, that question, what physical phenomena can be reproduced with classical path tracing, has not been adequately addressed. And in a recent publication, in its supplemental, we formally study that question. I think it has value to put formal limits on what classical, incoherent, and perfectly local path tracing can actually achieve. Feel free to check the work. I will just briefly summarize. What cannot be reproduced by such perfectly local and incoherent light transport frameworks are non-stationary effects. For example, all kinds of interference effects that arise by explicit scattering features. For example, scratches in a surface. Scratches in a surface can be appearance modeled to some satisfactory degree of accuracy, right? Some work have done very well. But to do so, you make particular assumptions about the properties of light. So it works in particular context under particular lighting conditions, and it does not generalize. It is fine for some applications, for some appearance modeling, but it's important to understand it doesn't always work. Other effects, like general diffractions by geometry, are very hard to approximate by such a framework in general. Also effects like non-time average effects like gross spectral interference, which is very relevant to acoustics, for example, are also very difficult to simulate. And I would like to stress that those deficiencies are there are formal limits. You cannot do better with a classical, local, and incoherent framework. It's not a question of coming up with a better BSDF model. It is the light transport framework itself that needs to be addressed. What this means is something in those two key properties will need to give. So to illustrate, let's consider a light particle, a ray of light, passing between a narrow geometric opening. So we know from basic physics that part of the total energy that would pass through that opening would need to diffract, meaning bend into shadowed regions. But with local particles, there is no oracle that can tell us that part of the energy carried and traced by this particle should have interacted with nearby geometry. Interactions are done at a point. Once that particle has passed through the opening, it would impart overestimated energy upon the target. Without incoherence, so if we did not have incoherence as a property, we could use other particles to correct this error via destructive interference. And indeed, some frameworks do just that. But in an incoherent framework, there's nothing we can do. And once that light particle passes through the opening and imparts overestimated energy upon the target, our simulation is wrong. What this discussion should illustrate is that it is enough to give up just one of those two key properties and achieve a strictly more powerful light transport framework. So I would like to do so in a way that is the least upsetting to classical sampling tools. So let's start with bilinear frameworks. These are frameworks that remain perfectly local, but what we did is give up incoherence. This kind of frameworks exists in the wild, and I will show you. So what bilinearity means is that passes continue to be point-to-point, so they are rays, and we may propagate light particles via some forms of ray tracing, but every pair of passes may interfere. Such frameworks, such bilinear formulations, apply to what I would call phase-carrying rays, so rays that propagate an underlying electromagnetic phase and then interfere on superposition. This arises in, for example, UTD-based frameworks. So UTD is a uniform theory of diffraction, which extends the geometric theory of diffraction. These are ray-based methods to simulate diffraction. As a prominent example, NVIDIA's excellent Shona framework builds upon UTD to simulate long wavelength diffractions. Other formalisms, for example, if you were to use a cross-spectral density from optical coherence directly of the Wigner distribution function, such formalisms have been proposed in the past. They also can be understood as phase-carrying rays that mutually interfere. I won't go into much details into the formalisms, it's less interesting. What is important is that once you give up incoherence, you get those kind of bilinear formulations where all pairs of particles mutually interfere. So if you consider the example on the right, we have two passes, X and Y. Both of them are observed by the sensor, say the same pixel of a camera. Classically, the observed intensity would just be the sum of the contribution of X plus the contribution of Y, and that's it. But in a bilinear framework, an additional bilinear interference term, which may take negative values, would arise. So this bilinear term is why I call such frameworks bilinear. Such frameworks have not been studied from the perspective of path tracing, and in recent work we generalized the classical path integral to the bilinear case, producing the following bilinear path integral. It is a very simple generalization, of course. We now simply integrate over all pairs of passes, and we consider their mutual contribution. The mutual contribution may be negative. So how the capital F, the mutual contribution function, would look depends on the formalism, but it is not very interesting to look into the details. What's important is that every pair of passes can interfere, and this path space formulation does generalize, it encompasses pretty much all bilinear. So all bilinear frameworks, all possible frameworks that do this kind of light transport. Our motivation in introducing this formulation is not so much in presenting a method to solve this integral. That is an interesting avenue for future work. So to design a path tracing algorithm for the bilinear case, and it might have practical implications if you come up with a good algorithm, because indeed those kind of light transports are being done today for RF simulation and long wavelength simulations. But my motivation for this formulation is to highlight the difficulties of path construction. So imagine that we sample a path X, right? And let's say that by itself, we did perfect path construction. It's a high contribution path. Excellent. But afterwards, a path Y is sampled, and the mutual contribution of X and Y might annihilate the contribution of X by itself and of Y by itself via interference. So we did perfect singular path construction, that we still wasted work and we have no contribution whatsoever. This cannot arise classically. What this means is that path construction is now always a global problem. And one needs to consider whenever you sample a path, whether another path might come and destructively interfere with your sample path. So let me illustrate. I use existing tools to render a simple double-slit diffraction pattern using current tools, and I will compare an incoherent framework where I use a free space diffraction BSDF, which I will talk a little bit more later. This free space diffraction BSDF lives in an incoherent framework, and I will compare it with a uniform theory of diffraction, so with a bilinear framework. So when we have very few samples, you can see that the incoherent framework looks like the typical Monte Carlo path tracing that we typically do, right? There is a lot of noise, but the fringes already begin to appear. You pretty much know where this is going. So we zoom in upon that highlighted small region that you can see on the right in the double-slit diffraction pattern. UTD, on the other hand, so the bilinear framework, is just noise because we didn't have enough samples to mutually interfere and produce the pattern. As I increase sample count, you can see that slowly the UTD will start, the fringes will start to appear. So what happens is that multiple samples will destructively interfere in order to chisel away at the diffraction pattern, right? While with the incoherent framework, that doesn't really happen. So incoherent framework, the pattern appears much earlier. And as you increase the samples, the point here is that the UTD will require an order of magnitude more samples in order to produce roughly similar level of noise. The more complex the scene in the light transport is, the more acute this problem becomes, right? Because it's going to happen at every scattering event. The deeper the passes, the more problematic this is. And this is the primary reason why existing bilinear light transport frameworks do not scale as well as classical path tracing. So that is all I'm going to say about bilinear frameworks. The conclusion is that sacrificing incoherence and allowing everything to interfere makes sampling difficult. There is room for very interesting future work, which I did not have time to explore, but I do find that giving up the ability to do local path construction, because effectively every sampling now is global, is detrimental. And I actually would like to sidestep the issue in its entirety. So if we do not give up incoherence, my other option is to give up locality, right? So the idea here is to sacrifice locality, but maybe to a degree, so not entirely. That is, we may define weak locality, which means that the spatial and angular distribution of light particles are no longer a Dirac, but some distributions with finite support. In more simple of terms, under weak locality, a light particle is no longer a ray which exists at a singular position and propagates into a singular direction, but instead it is a beam of light that at any time instant exists in a small region of space and propagates into a small solid entity. And that is weak locality. Light particles are a beam of light. So the question is then, how can we achieve a weakly local incoherent light transport framework? So the key here is to remember that we are never able to observe and measure everything about light. What we actually observe are the values we observe with the sensor are always integrated values. We integrate over the spatial and angular extents of the sensor. Those values can be small, but they're still not negligible compared to the wavelengths of light, as well over the spectral sensitivity of the sensor, and as well over time. And that is a lot of data that is being integrated or averaged way. Effectively, many interference effects are then aliased and are never observed. In the past, I employed optical coherence in order to decompose light into mutually incoherent samples, where no observable interference arises across such samples. This applies to forward, as in emitter to sensor light transport. Since then, the formulations have been unified into a bidirectional framework that is not limited to only forward tracing. The backward case, so when we trace light particle under time reverse dynamics from sensor to emitters, is actually easier to formulate, surprisingly, and it draws upon the realization that all our sensors are actually photoelectric sensors, which are essentially photon counters, and those sensors are very limited in their ability to do discrete statistical properties of light. So they're able to measure very limited things about light, which is good. It means a lot of things fall away, and we may achieve incoherence between samples. So feel free to check for more details those papers. I did not expect to have time to go into detail. But ultimately, some physics are going to be employed in order to decompose light into mutually incoherent, in terms of observable effects, weakly local light particles. These particles are beams, which quantifies the weak locality of light samples, which is the extent over which interference effects may be observed. All right, so in a bidirectional unified framework, today we use Gaussian electromagnetic beams as a light particle. Strictly speaking, a Gaussian has infinite tails, but of course we can just simply cut off the tails with arbitrarily good precision, giving well-confined, weakly local particles. The use of Gaussians is motivated by the physics that we use in order to decompose light into mutually incoherent samples. It is actually exact up to first principles in the backward case. It is a good approximation for many forward cases where you trace from emitters. So recently we have shown that it's very easy to see that the geometric envelope of such Gaussian beams are elliptical cones. So elliptical cones form a tight geometric envelope around the Gaussian beam, so where we cut off the tails. So in effect, the path tracing part, so the tracing part of the path tracing algorithm under our formulation of a weakly local framework reduces to propagating different elliptical conic frustum, which can be anisotropic, and intersecting it with the scene geometry. That is the geometric part. So instead of doing ray tracing, we do tracing of elliptical cones. Let me stress, this framework by design is incoherent. So you can do local path construction, you can do path sampling, as a matter of fact, in a way that is mostly unchanged or very similar to the classical case. And this is a huge win, right? Path tracing just applies in many cases very closely, almost without changes. Still, the loss of perfect locality does come with a cost. And let me talk a little bit about the difficulties. The difficulties start with the geometric aspects of such a path tracer before we even get to the details of implementing the optical formalisms. When I started implementing such a path tracer, so a more sophisticated version than a typical academic toy project, rather quickly I ran into seemingly trivial or seemingly, easy problems, but still very time consuming. For example, I couldn't find even decent intersection tests for elliptical cones with basic primitives like triangle or a bounding box, at least not ones that properly compute the intersection range which I needed. Other questions like how do we design accelerating data structures for cone traversal? They are probably similar to the ray case. There's no reason to believe that SAH-based structures will be poor for cone tracing, but there are still context-specific problems like a cone might contain an entire subtree, right? There's still things that need to be dealt with. Accelerating data structures have been investigated a little bit more in existing literature, but still not to the depths that we need. And there are other such problems. Since then, we have developed most of the geometric tools that we need. And Umut, who is a very strong undergraduate student, will be actually presenting that work this very week, I believe, in Pacific Graphics. Loss of locality gives rise to more problems. The interaction now of light with matter does not happen at singular point, but it actually happens across the region. The region where the elliptical cone intersects with geometry. It can be multiple triangles with different materials, so those are significantly more complex interactions. The design of appropriate multi-material scattering formalisms is still in its infancy, and that might be the hardest part about a non-local, so weakly local framework. So I will talk in the next slide only about one type of very interesting multi-material interactions, and otherwise I will just refer you to recent work. But before talking about that particular interaction, let me also mention that even basic materials models are very lacking today. Not all materials in a typical scene will be very interesting, right? Not everything is going to be a fancy diffracting aperture. If we want to simulate the interaction of RF energy with a city, most materials are actually going to be simple rough surfaces, right? So while in RF simulation, because of the long wavelengths, most of the scatter by surface will be highly specular, it is still not fully specular. There should be a coherent backscattered lobes, and there is going to be some scattering by the surface. And such materials are really lacking. There is no good models for such materials. There are also going to be other effects. So if you look at typical buildings, many will have, let's say, a brick siding. These bricks are roughly the size of the RF wavelengths, and they're not pure conductors. So there's going to be a layer of a periodic structure, and underneath there's going to be some concrete or wood substrate. So these surfaces are actually multi-layered surfaces with stationary statistics. They should not be represented by explicit geometry, but as a statistical material, so using some VSDF model. And if that sounds like the kind of stuff that computer graphics like, it's because it exactly is. It is a multi-layer material with stationary statistics. But computer graphics have not investigated these kind of materials from this kind of multi-layered materials from the perspective of wave optics that we need. Have not been enough in-depth work. So even this kind of rather basic materials are extremely lacking. Anyway, let me move on. A very interesting multi-material effect is diffraction by geometry. So where light passes, like as we saw before, between geometric objects and diffracts. Diffracting bends into the geometric, bends into the shadowed regions and diffract by the geometric edges of the objects. So due to its importance, existing implementations treat this separately. And there are two ways have been derived recently to handle this. For optical cases, there is a Fraunhofer-based edge-based diffraction PSDF that was published last year. This works very well when the apertures are small, at shorter wavelengths like optical wavelengths, but it's not very accurate for longer wavelengths. It is a more mature diffraction method, and it provides, current implementation provides very good sampling. It's just like another BSDF and produce excellent sampling. For more accurate simulations, what recently has been proposed are UTD-based ray bundles. What this means is that within our envelope of a beam, we actually have a bundle of UTD rays, and the mutual interference between those rays will produce the diffraction patterns, the diffraction effects. The UTD rays will be confined to that envelope of a beam, so there is still no cross-sample interference, which is very important, only within one sample. And those kind of formulation can, even so current implementation are not as mature, do multi-edge diffractions. So multi-diffractions across a path by multi-edge apertures, which no other software can really do. As very brief, some examples of how those diffractions look in a simulation. This is a very simple optical simulation using the Fraunhofer batch diffraction, where you have participating media and a very, very powerful collimated beam of light that is diffracted by a triple slit aperture. And you can see the pattern on the right. Slightly fancier scene is, again, you have a very powerful beam coming from the left. There is a screen with a double triangle aperture, and you get a diffraction pattern on the right, the typical triangular star diffraction pattern. This is also polychromatic. Those are the kind of optical diffractions implementations which already work and can do arbitrary rate renderings. It is more interesting in long wavelengths. So when you actually have diffraction around edges of buildings and those kind of effects. And recently I released a piece of software that does optical rendering, it does long wavelengths rendering, it does multiple things. It is incredibly early alpha. You're welcome to check it out, but not everything is still a mature implementation, especially the UTD-based ray bundles. This is still in its infancy. I am hoping to have another release early next year. There's still quite some work that has been also unpublished. Anyway, this is a piece of software that has been in the work for a year and a half, and it implements a lot of the research over the last few years. So to summarize, wave optical light transport under those tools that have been developed takes the route of being a weakly local incoherent light transport framework. So the incoherence allows us to do good sampling of passes and apply path tracing in a way that is very similar to classical case. Conceptually, the primary thing that change that the geometric proxies of light particles are no longer rays, they now become elliptical cones. Matter interactions are no longer at singular points, but over regions. I also forgot to say the path integral formulation has also been generalized to the weakly local case. I didn't show it because it is very similar to the classical case. We just no longer define a path as over points, but over regions, right? And because the addition is incoherent, we can do local importance sampling and apply many of the path sampling techniques that are done classically. And those are rather general light transport formalisms. They apply to a rather wide range of the electromagnetic spectrum. All right, so that's all for my part. All the publications that were mentioned, you can find them on my website. I'm happy to answer any questions. Thank you.